All right, so 11.6. Now we're going to talk about this notion of absolute versus conditional convergence. Absolute versus conditional convergence. We only talk about this for alternating series. So this can only even be a topic if we're talking about an alternating series. If we're not talking about an alternating series, then you wouldn't talk about this difference between absolute versus conditional convergence. So first of all, look at that theorem there. The third line there, it says if the series is absolutely convergent, then it is also conditionally convergent. Well, okay, it's good to know. The very top one there kind of gives the idea about what absolute convergence is. That just means that suppose you have a series that's alternating, you take the absolute value of that alternating series. In other words, you remove the negative terms, and then you find that it still converges. Well, that's called absolutely convergent. However, if you have an alternating series and you remove the negative terms, and then you find that that causes it to diverge where it converged before, like when it was before taking the negative terms away, that's what's called conditionally convergent. So let me just see if I can, let's do an example before we go delve more deeply into that. But look at this series here. And again, this only applies to alternating series. So if you don't have an alternating series, this is irrelevant. It doesn't apply at all. All right, now one other thing just to point out here is that when you see that cosine n pi, just think about what that actually produces for values. What are the outputs? Like when n is 1, then you get -1, right? Because the cosine of pi is -1. And then when n is 2, you get 2 pi, but the cosine of 2 pi is +1, right? And then you get 3 pi, which is -1, and then you get 4 pi, which is +1. So this produces just alternating -1 to 1. Meaning that it's just like a hidden version of an alternating series. And you can immediately replace it with what it's supposed to be once you realize that. So just don't let that throw you off. If you see cosine n pi on there, they might just be trying to throw you off and say, oh, maybe, is that an alternating series? It is. So anyway, if you see cosine n pi, just change it to -1 to the n. That's exactly the same thing. So anyway, this definitely establishes that we do have an alternating series here, right? Got that -1 to the n term on there. All right, so this is the way that you approach this idea of absolute versus conditional convergence. The first thing you would want to do is check the absolute value. And remember what happens when you take that absolute value. It's going to remove all the negative terms. In other words, that -1 to the n is just going to go away because now all the terms are positive, right? And now let's check that series. Well, that's easy to check because that's a p series, right? It diverges. P series, p equal to 1. Okay, so what happened? I took the absolute value and it diverged, okay? Well, that probably means that this thing has to be considered conditionally convergent. Although I do have to go back and check the original series as well, then check the series as given. That means the alternating series. Okay, now that means we have to check two things, right? We have to check is the n plus 1th term less than the nth term? I think that's pretty obviously true. Yeah, 1 over n plus 1 is definitely less than 1 over n. And then the other part of the alternating series test is that the limit of these non-negative terms has to be 0, and it clearly is. So it passes both parts of the alternating series test. So that means that this one converges, right? So this converges by the alternating series test. However, what doesn't converge is the absolute value, right? So the same series with absolute value diverges. And if you read what the definition of conditional convergence actually is, this is it, right? This is it. It says if it is convergent, but not absolutely convergent, okay? You see, it is convergent because I just did the alternating series test and showed that it converges. But when we took the absolute value, then it didn't, you see? And that's called conditional convergence, okay? So that's our conclusion. So this series is conditionally convergent. And now, why do we even care about this? Why do we care if a series is conditionally convergent versus absolutely convergent? What's the big deal anyway? Well, it turns out that conditional convergence is not a good thing. In fact, it's almost as bad as being a divergent series. In fact, if you have a conditionally convergent series, there's really not much you can do with it anyway, just as a divergent series. Why? Well, it turns out, and this is a very strange thing, but it turns out that if you have a conditionally convergent series, you can, by cleverly rearranging the terms, force it to converge to any number that you want to. Okay? So you could, and only by rearranging the terms. In fact, the book goes through this spiel if you want to check it out. It actually does it with a particular conditionally convergent series. So all you have to do is just rearrange the terms, and then you get it to converge to some other number than it did before. So in other words, it doesn't have a unique sum. You can make it converge to anything. So that's kind of a weird thing. It's like almost as bad as being divergent, like not converging to any number at all versus converging, but converging to any number that you want it to converge to. So that's the reason. These things are basically worthless as far as doing anything with them. So it's for the purposes of identifying them, just to say, oh, I have a conditionally convergent series here. There's probably not much I'm going to be able to do with it anyway. So that's about the only reason you might want to know. All right, let's check that second example there. So what are the steps? What's the first thing you would do? First thing, like we did in that last example, what do you want to check? First, check the absolute value for convergence, okay? So you're going to start out by checking the absolute value. Now realize that this type of question does require you to answer two, or to check two kind of different series, right? Notice that taking the absolute value makes it so that it's not an alternating series anymore. And so I have to use one of those other tests, check it, okay? This is actually a direct comparison. It's not really the same as some of those other ones. We don't even have to look and see what we're going to compare it to, but just jumping directly to direct comparison, I'm going to compare ln n over n to 1 over n, okay? Why 1 over n? Well, because we know what 1 over n does. 1 over n diverges. Well, why am I comparing it to that? Because it's very easy to make the comparison, right? ln n, I mean, the denominators are the same, right? So the only thing that matters is what's up top. How does ln n compare to 1? Well, isn't it always greater than 1? I mean, almost always, except for the first couple terms, perhaps. But yeah, it is going to be greater than 4, n greater than 2, I think, is where the cutoff is, but it really doesn't matter. So what does that mean? Being larger than a divergent series, it means that the thing diverges, right? So ln n over n diverges. Remember, we're doing a two-part check here, right? We're checking first the absolute value. Now, suppose that we were doing this same thing and we found out that this thing converged. Like if we took the absolute value and we found it converged, well, then we would be done, because look what it says up at the top, right? It says it's absolutely convergence if the absolute value also converges, right? So if we found that this thing converged, that would be, we would just stop right there and say this thing is absolutely convergent, and we're done. However, if it diverges like it did here, then you have to go on and do the other part. Then you have to check the original series, the alternating series that you started with, right? It's a different series because this is an alternating series, right? Whereas the absolute value wasn't. How do I check an alternating series? Well, I check it with the alternating series test. So I have to use a different test to check this one. And again, I would only do this provided that I got divergence on that first step. If I got convergence on the first step, I would be done. I wouldn't have to do this next part, the alternating series test. So what's the first part of the alternating series test? I need to show that ln n plus 1 is less than the terms of the original series. Now this one is a little bit harder to check, although I think Michael's method actually might be better here, just showing that the derivative is negative. So this is a bit tricky to show that that's true. Why is it tricky to show? Well, because look, we have an n plus 1 here. What does that affect? What effect does that have on that fraction? Adding stuff to the numerator has the effect of making the fraction bigger, right? So I'm not sure that that's true. But adding 1 to the denominator has the effect of making it smaller. So which one wins? Well, you can make the argument that the thing in the denominator is a polynomial and the thing in the numerator is a natural log. Polynomials grow faster than natural logs, so the the denominator term is actually going to win out there. A decent argument, and it's acceptable, in fact. But if you wanted to use Michael's method, you could show that the derivative is negative. And so you would say, well, what's the derivative of this thing? And then just show that that's negative. And then I think, let's see, that's just going to cancel. So you're going to just get 1 minus ln n over n squared. And you can see that that is negative provided that n, so this is definitely going to be less than 0 if n is, I think, bigger than 2. And so since it's definitely decreasing, that means that that an plus 1, less than an is definitely satisfied. So either way, it's true. It definitely works. That's the first part of the alternating series test. The second part is just to show that the limit as n goes to infinity of ln n over n is equal to 0, and that would be a L'Hopital rule situation. You could just, it's infinity over infinity. The derivative of ln n is 1 over n. The derivative of n is just 1, and then that definitely is 0. So that works. So in fact, both parts of this alternating series test check out, and so this thing converges, but it diverged when we took the absolute value, and so that means conditionally convergent. Okay, so everybody clear on this? When you are asked this question, what do? You have to check two different series. The first one is the absolute value of the given series. The second one is just the series itself without taking the absolute value, okay? And I should say you have to check up to 2, right? Because suppose that you got convergence when you did the absolute value. Well, then you would just be done. You just check one series and that's it. If you got divergence on that first one, then you have to go and check the second one. What if the ASTs did not satisfy both of them? Yeah, so that's a good question. Suppose that you got divergence when you did the absolute value, and then you went and checked the original series, and that also diverged. Well, there's actually 3 possible outcomes on this. If you see, what are the 3 possible outcomes? Outcome 1 is absolute convergence. You take the absolute value and you find it converges. Outcome number 2 is conditional convergence. That would be you take the absolute value of the first one, that diverge, and then the series itself converges, right? Outcome number 3, that is a possibility also, is that both of them diverge, right? You could get the series itself diverges and the absolute value diverges, everything diverges. In that case, you just say the whole series is divergent. So that's a possibility too. But good question, yeah. I was going to mention that, but thank you for reminding me. I totally forgot about that. It is possible for these ones to be completely divergent. All right, so this next test is the big one. This is the one that is the most useful, used the vast majority of the time. Ratio test. This is a good one. It's a bit harder to kind of use this test, but it is good because not only does it show convergence, it works for any type of series, including alternating series. And not only does it show convergence, but it also shows absolute convergence. So if this ratio test that we're about to do passes, then you can just say, well, it passed the ratio test, so therefore it's absolutely convergent. You don't even have to check for conditional convergence. So it works for a lot of different types of series. It shows absolute convergence. It works for even alternating series. So yeah, this is a big one. And this is the one that we're going to use most of the time for the power series that we see in the last 2 sections of this chapter. So let's use this second example as a motivator for the ratio test. We're going to check this thing for convergence. Now, I said that this is used far more than all the other tests, and it really is, but it only unfortunately works if the series that you're looking at has fast-growing terms. So this is for series with fast-growing terms. I'm going to put that in quotes because that's kind of a subjective term. What do we mean by that? Well, fast-growing just means anything faster than polynomial growth, okay? So I'll just put that in parentheses, faster than polynomial. And if you think about the way, the rates at which some of these functions grow, polynomials, I mean, they can grow pretty fast, right? But if you compare any polynomial to any exponential function, eventually the exponential is going to win. Exponential functions grow faster than polynomials, no question about it. So if you see any exponential functions in your series, you can use the ratio test. Well, what grows even faster than exponential growth? Factorial growth is even faster. Factorial growth. And so if you see any factorials in your series, ratio test is going to work. And then there's even one that's faster still than factorial growth, and that is n to the power of n. This is like n to the power of n. That's the fastest growing function, at least I guess elementary function that we can come up with, n to the n. So if you see that one, definitely. In fact, n to the n is one where you might actually want to use the root test, which is another test we'll see in a second here. But anyway, any of these terms that have fast growers like polynomial, or I mean exponential, factorial, n to the n, anything like that. So how does it work? So it's a limit that we have to find. And we have to find another limit as we go to infinity, and it's the limit of the absolute value. You can see what it says right there, an plus 1 over an. That we have to find that limit. Well, what's an plus 1? An plus 1 is what you get when you replace the n's with n plus 1s, right? So n plus 1 factorial, and 5 to the power of n plus 1. Now, just like with that limit comparison test, remember you had to do this ratio also? Dividing by the nth term is the same as multiplying by the reciprocal of the nth term. So that's typically what we do just right away. Instead of making a division, we just make it a multiplication. It's easier to deal with. So that we have to find this limit. That's the goal. Find this limit. All right, so this is where we have to kind of really think about what these factorials are and how do we simplify them. And we really have to remember our exponent laws so we can simplify this kind of stuff. All right, so I'm going to go ahead and take care of the 5 to the n and stuff like that, and then I'm going to show you how to deal with those factorials. And I'm going to drop the absolute value bars because they don't matter anymore. There's no negative terms here. But so remember, our laws of exponents say that 5 to the n plus 1 is the same as 5 times 5 to the n. Everybody okay with that? So I'm just saying this is equal to this, right? Because when you have x to the n plus m, it's the same as x to the n times x to the m, right? And in this case, the m is 1. So 5 to the first times 5 to the n. All right, so that means we can cancel these, right? And we can take that 1/5 out of there. So I'm going to move the 1/5 to the front. Now, with these factorials, this is where, and this is the first time you're probably seeing this, how do we simplify factorials? So this is, at this point, I'm just going to say, what is n plus 1 factorial? What does it actually mean? Well, it means that we're going to take n plus 1, and we're going to multiply it by the number, all of the number integers that come before it, right? So that's n times n minus 1, n minus 2, right? And this is just going to keep going. We don't know what n is, but we have to assume that it's a finite number. Eventually, we're going to get down to that, right? That's what a factorial is. It's that number multiplied by every single integer that comes before it all the way down to 1, all right? But if you look at this, what is this? What is that? N times n minus 1 times n minus 2 and so on all the way down to 3, 2, 1. That's n factorial, exactly. So what we can do is we can rewrite this as n plus 1 times n factorial. You see that? And you can in fact do that with any factorial. You can chop the first one off and then make the one right before it the factorial, you see? Or I could even do that with the first 2 or 3 if I wanted to, or the first finite number, really. And so with that in mind, how should I finish this? I should write the n plus 1 factorial as n plus 1 times n factorial. And then I still have that n factorial there. But look what happens there. Those now can cancel, right? And now I'm just left with this limit, right? The limit of n plus 1. Well, what's that limit? That's infinity, right? I'm going to infinity. I got an n plus 1 there. The 1/5 isn't going to do anything, so infinity. All right, and so you see, what are the conclusion? What do we want to see for the ratio test to be able to make some kind of conclusion? This limit, if it's infinity, it says right there on step 2, right? If it's infinity, it diverges, right? So we're done. We've just shown that this thing diverges. So the test itself is a bit involved. It's a bit more involved than some of those other ones. You have to find this limit, and that sometimes can be kind of tricky. But once you've found it, then that's it. All right, so let's try example 3. You can see on that one, again, it's got exponential terms, so clearly the ratio test is justified here. By the way, what do you think is going to happen? Like, why do we want to see those fast-growing terms? What do you think is going to happen if we attempt to use the ratio test that doesn't have fast-growing terms? So, like, suppose it was just polynomial growth terms and that's it. Well, if you see, there's one little problem with the ratio test, and that's step 3, right? Or condition 3, I guess, if you look at the ratio test 3 things there. The third one is the problem. The ratio test is inconclusive if that limit that we're trying to find is 1. If you see, you go through your whole steps, you take that limit, and you find that the limit is 1, well, that unfortunately means nothing. That means that the series could either diverge or converge. You wouldn't, and you can't know until you try some other test. And so what do you think is going to happen if you attempt to do a ratio test on a series that doesn't have fast-growing terms? Well, that limit, guess what it's going to be? Almost guaranteed, it's going to be 1. And so that's the problem with the ratio test, and why those why we want to see fast-growing terms. So just try to remember that. If you do get 1 out of the ratio test, that means probably you tried to do it on a series that doesn't have any fast-growing terms. All right, so let's take a look at this one. So ratio test, we want to take the limit as n goes to infinity of absolute value of n plus 1, an plus 1, that means all the n's replaced with n plus 1s, divided by all the nth term, divided by is the same as multiplying by the reciprocal, so we flip over the original terms, and this is the limit that we have to find. So this is not an easy limit. This is what I mean by the ratio test sometimes being a bit tricky. The test itself is a little bit harder than some of these other tests because sometimes these limits, unfortunately, are not very nice. We'll see why this one is not so nice. But again, right away we would use our properties of exponents to rewrite these, and then the rest of this stuff just stays the same. Okay, so right away what we can do is see that these 7 to the n terms are going to cancel. That leaves us with, in fact, the 7 there, I'm just going to go ahead and take that out. I'm talking about this 7 right here. That 7 can be brought out front because it's just a constant. So I'll take that out front, and that leaves us with the 3 to the n plus 4 to the n over this stuff. Okay, and again, you can probably see, yeah, this is not a nice limit to find. So what do you guys think? What do you think is the way to find this particular limit? Yeah, unfortunately, L'Hopital's rule is not going to work because no matter how many derivatives that you take, well, what's going to happen on these? These are all exponential functions, right? When you take derivatives of exponential functions, what do you keep getting? You just keep getting the same function back with that ln of whatever the base is. But no matter how many derivatives we take, we're just going to keep getting the same thing, basically. So it's not gonna go away, unfortunately. I guess probably best for me to just show you because it's a hard one to figure out, like what you actually have to do. The trick is to actually factor out this 4 to the n here. And let's see what happens when you do that. If you factor out the 4 to the n, then that means that first term is going to have to be that, right? You take the 4 to the something away that wasn't there to begin with, and you have to put it in the denominator. And then you're going to get a plus 1. And I'm going to do the same thing here. I'm going to factor out a 4 to the n. And what's that going to do? That's going to leave us 3 times 3 to the n over 4 to the n. So why did we do that? Well, now we can cancel those, which is kind of nice. And then realize that the 3 to the n over the 4 to the n, you can rewrite that like this. 3 to the n over 4 to the n is the same as 3/4 to the n, right? 3/4 to the n. And then in the denominator, same thing. Okay, now think about what happens when you take the limit as n goes to infinity of this fraction that's less than 1, right? This fraction that's less than 1. What happens to that when you go to infinity, to those two terms? Yeah, they go to 0, exactly. And so both of those are going to go to 0. This is gone, this is gone. And that's it. That's the key there, right? Now that those are gone, we're done, right? And what's left? The 7 we had out front, and then the 4 that's left in the denominator. So the limit is 7/4. And again, the key here, what's true about 7/4 in particular, it's bigger than 1. And if you look at the second thing on the ratio test there, if this limit is bigger than 1, that's divergence. All right, so we've got 2 divergent ones so far. All right, now the root test. It's just kind of I would really just call this a variant of the ratio test. Everything about it is almost the same except for like what you actually have to do, but all the conclusions are the same, as in, if you get it less than 1, it's convergent. If it's bigger than 1, it diverges. If it's 1, it's inconclusive. So it's kind of a variant on the ratio test. It's used less frequently than the ratio test. In fact, the only time you would ever even really use the root test is if you have a function that looks like this example 4. And what's the key about this function? It's raised to the nth power. That's the key that you're going to use the root test here. So if you have some term, whatever the heck it is, and it's raised to the nth power, or even some, 2n or 3n or something like that, that is the key right there. If you see that n up there in the exponent, that's a root test problem, okay? And again, that's the only time you would really use the root test is if you see that there. If it's not there, it's the ratio test or some other test besides that. And so why does the root test work so well on series like this? Well, you can see what the root test tells you to do. It says take the limit of what? It says to take the limit of the nth root of the terms of the series. Well, since I have that nth power there, you can kind of see why taking the nth root might be beneficial, right? If I have an nth power and then I take an nth root of an nth power, well, they cancel each other out, right? So the nth root and the nth power cancel, and you're just left with this. Basically, whatever's under that radical is what's left. And that limit is pretty easy in this case, right? It's just 3. And 3 is bigger than 1, and so diverges.